All right, next we're going to move into taking a look at what happens when we have repeated linear factors. The remark that describes how to do it in in general with any number of factors. It's all well and good and it's true, but that's not necessarily the best way to learn from it. It's not necessarily very illuminating. So, best to start with this example 3, where we're just going to write down the actual forms for each of these, and you'll get the sense very quickly what you do and what the pattern is. So here we have a repeated linear factor. This x plus 2 is being squared. So what we will end up doing is we will have a over x plus 2 plus we would have a b over x plus 2 squared. Okay? So we essentially start with the factor itself, x plus 2, and then we will work our way up until we reach the power that we have. That's our stopping place. So what did we mean? Well, let's see it in action here. What happens if it's x plus 2 cubed? Well, this would be a over x plus 2. Always start with your factor itself, and then you increase the power on it for each new term. And then once you finally reach the power that you have in your expression, that's where you stop. So we would have a over x plus 2 plus b over x plus 2 quantity squared, and then another constant, c over x plus 2 quantity cubed. All right, now for this third one, let's see here. Now we have a blend. We've got we have two repeated linear factors, right? They are distinct in the sense that, we don't have a total of 5 repeated of the same kind. We have 2 different factors, and each of them is repeated. And then we've got this distinct factor, x minus 1 to the first power. So the decomposition for this one all right, it's a little bit to write out. This would end up being, well, the distinct linear factor is just the constant over itself. Now for the x minus 2 terms, we're going to have x minus 2 to the first power, x minus 2 squared, plus an x minus 2 quantity cubed. And now doesn't matter how you write your constants, whether you want to use A1, A2, A3, or you want to use lowercase a, b, c. It is customary to use capital letters and starting with A and going alphabetically. Nothing wrong with lowercase letters, but I don't know. Stylistically, it's very common to see capital letters used here. So we have the distinct linear factor contribution, the 3 factors that we get contributed from the x minus 2 to the third term. Now for this other repeated linear factors, x plus 7 squared, that will contribute 2 more factors, x plus 7 and x plus 7 quantity squared. So continuing E and F. So that one's pretty gnarly. This would be a crazy one to figure out. Don't worry, you won't have to do ones like that. Well, at least not where you have to figure out what all the A, B, C, and so on and so forth are. You may very well see a question where we ask you to write this down, just the general form of something gnarly like that. Okay? So here, let's see, this would be, let's copy down the numerator and denominator, x plus 4 quantity to the fourth. Again, a little bit obnoxious, but it's to hammer home a point. So a over x plus 4, b over x plus 4 squared, plus c over x plus 4 cubed, plus d over x plus 4 to the fourth. And then lastly, 2x over x minus 10 cubed times x plus 1 squared. This is a over x minus 10, b over x minus 10 squared, plus c over x minus 10 cubed, plus d over x plus 1. Lastly, we're going to have e over x plus 1 quantity squared. Okay. So let's take a look at example 4 here, putting this into practice. Our rational expression is already factored for us. We see that we've got a single linear factor, x plus 1, and then we have a repeated linear factor. So let's go ahead and write down this decomposition in terms of the undetermined coefficients. So copying down the rational expression, we don't actually need the integral. This is an algebraic sort of algorithm, so we'll take care of that. So the distinct linear factors will contribute. So we have a over x minus 1 plus b over x minus 1 quantity squared, and then our single linear factor will contribute a term c over x plus 1. Again, we are going to multiply by the entire denominator here, which will clear the fractions. So we'll have 4x on the left, and then the commonalities will cancel. And this is where it's a little bit, it could potentially be slightly misleading, because the x minus 1 is in common here, but when we multiply by x minus 1's quantity squared x plus 1, it is true that the commonality will cancel, but because we have two copies of this commonality, we only have one copy in the bottom. So you're only going to lose one copy. So here, this would end up being a times the remaining x minus 1 and the thing that wasn't in common, x plus 1. Here, for the b term, there are 2 in the bottom, so they will cancel with all of these terms here. So we'd be left over with just x plus 1. And then with c, the x plus 1's will cancel, and we'll be left with x minus 1 quantity squared. All right, so now let's go ahead and plug in some clever values. Let's do x equals negative 1. So if we do x equals negative 1, this term cancels, this term cancels, and we're left with the c term. So this will be negative 4 on the left equals c times negative 2 quantity squared, which is 4. So c is equal to negative 1. Plugging in positive 1, this gives us 4 on the left-hand side. And now plugging in positive 1 is going to cancel this term and this term. We'll be left with the b term, which is going to be 2b. So b is 2. So here we can see that this plugging in nice values of x doesn't always yield exactly what we saw in the first example or two, because there's nothing we can plug in here, there's nothing we can plug into this entire equation that will cancel b and c but not cancel a. There's no way we can plug in something and keep a simultaneously canceling b and c terms. But that's okay. You can just plug in another nice number for x and maybe not have everything canceled out magically, but you can still have something that's way nicer looking and easier to work with. So here is why I will plug in a nice value of x equals 0. The left-hand side will turn into 0, and then the right-hand side will turn into negative a plus b plus c. And now we know what b and c are. b is 2, c is minus 1. So a, if I add it to the other side, is equal to 1. So it's still not a lot of work, and it still is a very quick way to figure out your coefficients. So I would use that method. Okay, so now we can go ahead and set up our integral. So this original integral is equal to the sum of 3 other integrals. 1 over x minus 1. And we don't even need 3 separate integrals. I could just write them out as a sum. So a over x minus 1 plus 2 over x minus 1 quantity squared minus 1 over x plus 1. So this would be natural log absolute x minus 1. Here, this would be, we can sort of think of this as 2u to the negative 2 du, with u equals x minus 1 and du equals dx. So then this would be 2 over negative 1 u to the negative 1 plus c. So this would be negative 2 over u plus c. So this would be negative 2 over u, and u is x minus 1, minus natural log absolute x plus 1 plus c. Again, you don't have to simplify things, but I have a hard time not doing it when you have natural logs because they simplify so nicely. So I'll write this as natural log absolute x minus 1 over x plus 1 minus 2 over x minus 1 plus c. And there you have it.